Welcome back. In the previous video, we understood velocity diagrams. Now we move to acceleration diagrams. Many students feel that the acceleration diagram is difficult, but actually it is just velocity diagram plus two additional components. Let us understand this carefully. First, we have to define what is the acceleration. The acceleration is the rate of change of velocity. Velocity can change in two ways. Either it is change in magnitude or change in direction. If either happens, the acceleration is exist. If change in magnitude happens, then tangential acceleration exists. If change in direction happens, then radial acceleration exists. The tangential acceleration is represented with AT. The radial acceleration is represented with AR. Now, consider a simple link OA. Now, it rotates about the fixed point O with an angular velocity of omega and angular acceleration of alpha. The velocity of A is tangent to the path. This is the tangent. This is the velocity of A. The velocity of A is tangent to the path. Now, if omega is constant, is velocity is changing? Yes. The direction of velocity is continuously changing. Just see here, at this position, the direction is here, and at this position, the velocity direction is here. The direction of velocity at this position is like this, and here it is like this. That means if omega is constant, the direction of velocity is changing. If the direction of velocity is changed, then the radial acceleration will be exist. Now, in which direction the radial acceleration is exist? This is the radial acceleration. The radial acceleration is exist because the direction of velocity is changing. It is always directed towards the center of rotation. Just see here, the radial acceleration is always directed towards the center of rotation. Now, suppose if omega is changing, that means we are increasing the omega. What will happen? The velocity magnitude will change. The velocity is magnitude change, then the tangential acceleration component will exist. The tangential component of acceleration is perpendicular to the link OA. That means it is same direction of velocity, which is AT. Now, how we can calculate the tangential component and the radial component? The radial component of acceleration that we can calculate with omega square into r. The tangential component of this link OA we can calculate with the help of this formula, which is alpha into r. Here r is the length of the link. Suppose if the angular acceleration of the crank, okay, here it is a rotating element. If angular angular acceleration, which is alpha is equal to 0, then the tangential component of acceleration becomes 0. The radial component of acceleration is omega square r, as we know that the linear velocity of the link is omega into r. That means omega is equal to velocity upon radius. That means the radial component of acceleration is equal to v square upon r square multiply with r, which is equal to v square upon r. That means the relation between the linear velocity and radial component of acceleration is v square upon r. Here r is the length of the link. If omega is available, we can utilize this formula, which is omega square r. Or if omega is not available, we can use v square by r. Now let's see that how to draw the acceleration diagram for a link AB. Before proceeding that, just we can recollect the radial component of acceleration is always directed towards the center of rotation. The tangential component is always perpendicular to the link OA here. Okay, generally it is perpendicular to the link. We can calculate the magnitude of radial component by using omega square r or v square by r. The tangential component of the link calculated from alpha into r. First, start with random point O dash. First, calculate the magnitude of radial component, because the omega will be known to us. From that, we can calculate AR is equal to omega square into r. Take suitable scale, draw a line which is parallel to OA. And again, we know that it is towards the center of rotation. Here the center of rotation is point O. That's why I draw downside. Let us take the point X. O dash X represent the radial component of acceleration. Then draw a perpendicular vector from point X. The magnitude of this length of x and A dash is the tangential component of acceleration, which we can calculate from the alpha into link length, which is OA. Suppose alpha is not given, that means AT value becomes 0. That means O dash X will be the your acceleration of the link OA. In this case, we have radial component as well as tangential component. Then we can join these 2 points, which is A dash and O dash. This is the final resultant acceleration of A with respect to O. Okay, in the next video, we can see some examples on the various mechanisms.